So, what I'm going to talk today is about how you bring a machine into a real working thing. So, first of all, we always used to draw machines on paper and with pencil and all. Then, how do you bring a machine working in the shop floor? So, how many people have visited shop floors? All of you have visited a shop floor. A shop floor means where you see the machines working. You have seen a real machine working. Okay, so most of you would have. Yeah. Okay, nice. So when you want to, you see a machine working. So what is the working thing? You mean there is power in it. Something is going on, happening inside it. So it has a brain of its own. It knows what to do inside. So that's when you call the machine is working. So that is when automation is working inside it. So when we build a machine in Titan, a lot of thought goes inside it as to how you design a machine, what you have to bring from a paper, pencil concept to the actual, how does it know when to start, what to do in case of an emergency, what to do if something comes in front of it, or a lot of thought goes inside it. So I'll just share what all things go inside the machine which is working. So what do you understand by automation in general? Okay, before that, I'd like to tell about the agenda that I have taken so much pain preparing. This is one typical example of a machine working in shop floor. This is, you recognize these, it's a car making factory. That's nice, I never thought of that. So, these are those robots which, a car comes out of an assembly line in close to, a Ford comes out in close to 27 seconds and a Maruti Swift comes out in 53 seconds. So every car that comes out of the automation line is, in the assembly process. So all of you would have read that Henry Ford designed the assembly line, and that is how cars, change the history of car making in factories. So that is how a car comes out of a factory. And Toyota, you would have heard of Toyota cars. Like Toyota has revolutionized the way the car making happens. It has a bypass line for everything that happens that could go wrong in a car making factory, right? So it's like if something is happening, some car is getting manufactured and at some point of time it stops, then Toyota has bypassed it to some other. So Toyota cars have revolutionized the way they had dealt with car making is like totally the new thing in industry. And okay, so this is the examples of how automation happens in everyday life. And then I talk about what is automation and how do we see industrial automation as divided into which all classes. And then the next concept is about high-speed automation. So when you talk about high-speed automation, all of you have heard of high-speed automation. Do you relate to high-speed automation? Yeah, you can give anything. Okay, even I am new, so it doesn't really matter what I know or not. So this session is like, I learn from you and you learn from me. And I can only speak if you can also say something back to me. You can say anything. I'm not going to, really remember much of it. You just can say and you can speak anything.
Because one of the criteria for mass volume, so it's all the automation will come under the heading of the.
No, not that. That is not true. That's what we think, that automation should happen in high speed. That is why the word automation. But then high speed automation is totally new sector altogether. It's like you have things which goes at a very high speed, at a cycle time of close to 1 second. Do you understand cycle time?
Yes.
That's nice. Do you understand lead time?
Yeah.
Okay, the cycle time that we talk about in a factory. Yes, sir.
The power plants, the startup and the shutdown of the plant,
Takes a little bit.
it goes through the high-speed automation. There the cycle time is 1 millisecond.
Mm-hmm.
That is the sequence of events are there which are recorded per 1 millisecond time.
Right,
This is
right.
less than 1 second.
Right. So there are many such examples. Now, when I talk of automation, because I come from the factory automation part, so we have, like, there's something different between process automation and factory automation. Like, what we do is designing machines. In process automation, you'll see that machines are all interconnected and the entire factory is connected to one controller. That is also a type of automation. So there are different types of industrial automation. Now, even anything that you call, even your coffee machine is an example of an automation. Have you heard of building automation, lighting automation? Okay, now these lights that you see on the top of you, these lights could dim and go high or low according to where you're standing and where you're not. Have you guys come across this? Yeah, there are, and these can also be connected in apps that you can access right on your phone. and you can see it like where you want to dim it, where you do not want. Like I am now going to the bathroom, so I want the light on high in the bathroom, or whichever. It is, everything is now at a different level altogether. So automation is a part of you everywhere you go. Then then high-speed automation is generally, we use high-speed automation to deal with medical disposables, like things which are required at a very large volume and they always have a high demand in the industry. So you have to keep on producing them at such high production levels that if suppose the machine stops, or if the downtime of the machine is really high, then your customer will not be pleased. So that is when high-speed automation comes into picture. Then finally, I'll talk about forking beam chassis that we have developed at Titan to target these industries where there's a huge production volume is required and a huge demand is on the consumer side. So that is all about today's agenda. So you can identify these. Yeah, the second one is a conveyor. The first one, it's a vending machine.
Water tap. This is ATM.
Yes.
Metro entrance.
Right.
Entrance, right?
And nobody identified this one. This is Britannia treat.
Britannia biscuit.
Right. But that's not important here. The thing is, putting them in a conveyor and then having them automated is not an easy job because it's a very sticky thing and it's food. So food always has regulations. You always have hygiene standards to be maintained in food. So everything that comes in contact with anything that will come in contact with humans at the end will have a set of standards known as hygienic design standards. So that is also, this one you guys identified, right? What is different in the water tap? Yeah. So all of you have seen this, use this. When I was little, I used to think, where is the knob to turn it off? Right? So that's a sensor. You just put it, it's like you put it and you just remove it and it works. So this one, of course, is your everyday life routine. This one, and if any of you have operated a home automation? Nice. So what was your experience with the home automation?
Actually, I haven't seen that yet, but on the internet and on the TV, I have seen that all the things in house are automated using a mobile phone or remote control, and they can automate the lights. Whenever someone passes through the corridor, the lights will automatically switch on, and after the passage is over, the lights were gone off.
Right.
All these kind of things I have seen.
Right. That's nice. So you would have heard of conveyor belt sushi. Anybody has heard of not sushi, not conveyor belt? At least the whole concept. Okay, all of us are aware of what sushi is. Sushi is a food. Conveyor belt is the belt that goes in factory automation line, and Japan is a country. So when all of you put this together, it comes conveyor belt sushi in Japan. If you have not seen it, I would like to show this to you. It's how Japan has integrated conveyor belts in their restaurants.
How they know that which food is for them?
I beg your pardon, sir?
How they come to know that which plate is for them?
Oh no, it is all pre-ordered. There's a
That's
screen.
fine. I can pick up something pre-ordered for someone else.
No, whatever you pick up, there's a sensor attached to it. Whatever you pick up, you'll be billed for that. So it's like anybody can pick up anything, but you'll be billed. And if you have a special order, then it will stop only at your place. It will just whiz through it in the special order line.
That's more important, na?
So this is one thing that Japan has done in many sushi restaurants, and I guess this is like you walk in and there is automation in every place that you go to eat. This is like whatever you have to do without human intervention is automation. You people may not take notes, it is not that important. I will give it to you later. What you really do and physically experience is kind of more important. So, the types of automation. So, generally automation is divided into 3 basic types when we talk of industrial automation. We'll talk about discrete, we talk about process, and we talk about batch automation. This is how the industries are classified. So when you have discrete automation, it means that one part comes out after the process is complete. So in automobiles, we have one car coming out of the line after the process is complete. So that is discrete. So you process the component parts, anything that goes inside the car, and the things which go inside the car are automated in a separate line. And that is also another form of discrete. So all those cars which come under the finished goods, and then you have an automobile coming out of the line, so that is a discrete automation. When you talk about process automation, you have raw materials which come in a continuous stream of products, like you have in oil and gas. You cannot separate like one drop of oil as discrete. So that is like the process. The entire process is automated, and you have the oil and gas coming out of the line. Then when you talk of batch, you generally say biscuits in packets. Like I have processed like 10 batches of biscuits or 10 batches of say tablets. So those kind of industries are batch automation. So that is how we categorize the industries types in automation. Now, when you talk of high-speed automation, this is something that is done at close to less than 1 second or close to 1 second, where you need very high speed in assembly, in packaging. So everything you may not be able to, even be able to observe it. So what is very important in high speed automation? Yeah, that can do up to 1,000 parts per minute as of whatever has been proved. Now, high speed automation requires very reliable. Now, why reliable? Because every time a process goes wrong, if a high speed automation stops at any point during the time, you have a huge loss in production. Then when a regular machine stops. Because if it's a high speed and then you see there's a large loss of volume. But when you require reliability, you have to do very precision engineering every time. So say you're thinking of something high speed here or something else. Right. So when you're thinking of really reliable automation every time, then you have to be very precise and very specific as to where you want this part to go at this point of time. So high-speed automation, the time period is divided into very minute microseconds. So at this point of time, I want this thing happening. At this point of time, I want this thing happening. So it is like this. You have to, when you design the machine, to keep that thing in mind, that during this period to this period, what all parts of the machine should be at which all points. So that is very important in high-speed automation. Now examples where high-speed automation are used mostly are FMCGs, that is fast-moving consumer goods, then pharmaceuticals and medical disposables. PCBs, yeah, that is also kind of high speed. So as of now, actually, when we talk about our machines as an example, then mostly we target these industries. PCBs are also run in very high speed because of the large production volume that is required. So anybody has any questions till this end? You can ask whatever you want. Even the spelling of automation would do. Okay. Now, this is something that Titan has designed, a walking beam chassis. Okay, so walking, you know what is walking? Beam here stands for what do you call a structure? Any structure we call a beam. In our factory we use aluminium beams and all those, so that's called a beam. Beam is not a light beam. Okay, so beam, when you talk of beam, just take this as an example. I could have told that, but then it feels better drawing it. So this is a beam. Okay? Okay, yeah, so we were talking about walking beam chassis. Now, what happens in walking beam chassis is, a chassis, you've heard of chassis? Most of you are aware, okay. So chassis is like a structure. When we, in automobile industries, when we talk of, say, suppose this is the car body, then the body of it, the base part of it is what we call a chassis. When we talk about walking beam chassis, we mean that it's the structure and the walking beam are two beams that we have used, one for walking and one for locking. So there are two beams that are used. Beams as in, you may call those the beam that I showed. So the walking beam chassis is an example of a structure where we have put all these technologies together. So this structure is like a standalone modular machine. Now, what is it basically? It is a linear assembly. Linear, you have heard of linear. Linear is a line that you have studied in physics. So linear is a line and rotary is a circle. So when you talk of linear, it means that the assembly goes on happening from one point to another to another. So it goes in a line. So that is how you call it as linear assembly. And automated is automated with integration of standard pick and place modules. So how many of you heard of pick and place? Like these words individually, all of you have heard. Have you heard of pick and place modules?
Everyone would have.
Right? So pick.
There's a robotic arm which pick and then place.
It can be any arm.
Yeah.
So you just, that's an example. So pick and place is you pick something and you place something. That is what pick and place is. How it is done, why it is done that, and why it is not done that, what can be done to improve. It can be done by robotics, by pneumatics, by servo, by cam, by anything. It is just that what is pick and place, what is to be done, and at what point of time it should be done. Then it has defined flexibility and modularity. You have heard of modularity? Modules. Every chapter is divided into different modules in any book. So suppose there is a book of 100 pages. So when we call of modularity, it is like say 5 modules. So each module has 5 pages each. So that means it has 5 modules. And each module is independent of each other, but still it is connected to the book as a whole. So that is when we call as modularity. So today, if you have one such machine, suppose this is one machine and it has suppose 6 parts in it, you can duplicate this machine into another machine and which will also have 6 parts. So this is one module, that is also one module. So today if you are producing only say 20 components with this machine, if you connect that one with it, you have 2 modules now and you can produce 40 parts. So this machine is a modular machine. So you keep on connecting as many modules you want and keep on producing as many, then double the number of parts that you are producing today. Then you have the cycle time that we have targeted was 1, but then due to design specifications we had to come down to 1, go up to 1.2. So till 1.2 to 2.4 we have tested on our prototype. The number of parts that we have worked with was 25 to 50 parts per minute was the maximum that we have tested in our prototype design. Then the indexing accuracy of 50 microns. Indexing, you heard of indexing? Okay, nothing to worry, even I learned indexing in my second year also. So indexing is like, suppose this is the conveyor. So when you talk of indexing, you have a part moving from one point to another point at fixed durations of time. Like when I say, suppose this part is moving on the indexing table, then it goes from one point to another, it stays at that point, and then it goes again to the next point, it stays at that point. So indexing means it goes and then stops, again goes and again stops. That is how indexing is achieved on a linear table, right? So, so what is your experiences with indexing? I'm just using the same technique you told me about to ask questions. Right. So, generally indexing we do in rotary tables or linear tables. That is how indexing is generally done, to have different processes occurring at the point where the part is stopped during the line. Now, indexing accuracy means whenever you have 2 parts produced on a machine. Now, indexing would mean, suppose this is the line and these are 2 pallets. You understand pallets? Pallets is like this, so any part that comes on it, pallet is just like a sofa to sit for the components. So components will come sitting on the pallet in the line, right? So this is pallet 1 and this is pallet 2. So when you have some indexing going on, these 2 pallets should stop at the same distance from each other every time. If this doesn't happen, then the tools that come down from here to do some processing on the pallet will have an offset, and every time this happens you lose, because of the offset there will be a backlash developed in the system and the pallet will, the processing will not happen at the same point of time everywhere. So this accuracy is very important, that you maintain that accuracy, that shift in pallets every time as the same. So in our case it is 50 micron that we have tried to achieve. Do you guys understand it now, or should I use more simpler example?
Go ahead.
Okay.
It's clear.
I did that alone. Okay. So this may be a little difficult. It was very difficult for me to understand when I tried it the first time. Do you understand a cam?
So many cams are there. Which cam you?
A general cam. Let us take any.
It's a computer manufacturing.
That is a very high degree of cam. Cam as in the cam follower. Yes, cam and follower. No, I thought you were talking about the different types of cam. Okay.
Automation.
Yeah, so see, I'm not from a mechanical background, so I just talk of cam follower as a general cam, okay? So when we talk of a cam, we have used the cam mechanism to do the pick and place. So in this walking beam chassis, you have to accomplish the pick and place during when two things are, like all the four stations are doing the pick and place at one point of time. At one point of time, they are stopping and inspection is happening. So everything is pretty much synchronized. So all the cams need to be synchronized with each other. And so there is one master cam, there is a slave cam. So in our machine, we have 3 cams. So we have 2 servo motors and 3 cams. So okay, you got that inside? Okay. Yeah. Now, when you have one servo motor, the servo motor drives the indexing motor. So you have, so this is suppose the walking beam and this is suppose the locking beam. And you'll have the motor here. And here will be the main cam. We have 4 pick and place modules, so we have 4 of these cams. Now these cams are connected mechanically, right? And the main cam motor drives these cams through the encoder and all those belt mechanisms and everything. So it's kind of driving these cams. And these cams are doing the pick and place. So all of these have the pneumatics attached to it, the cylinders which do the pick and place. And then there is, these are 2 beams that we have. You can take either one as walking and either one as locking. Now, these beams are driven by another servo motor, which you can call it as the indexing motor. Now, when the indexing servo motor moves in, suppose the servo motor can either move in anti-clockwise, clockwise, or it can stop, right? So it can move, when it moves in suppose clockwise, the walking beam goes to the front, and then again when it moves, it stops there, and then the locking beam will go up to engage with the pallets. So the pallets are all coming in with a conveyor. So all this is a conveyor here. Is it gone too beyond? Are you guys getting it?
Yes.
That's not the truth. I know I didn't ever get it. Okay, so this is the servo motor. When it rotates in one direction, the walking beam moves forward and then it stops.
You don't have its sketch?
I have the sketch.
Okay.
Okay, fine. I'll show the sketch then. Or I'll just show you the prototype ones. Maybe it will be better then. See, the 4 are doing it simultaneously. These are the pallets. This is the conveyor. And this was just a prototype. So machine is covered. It's not like this. And these are nuts, as you can see. And these 2 conveyors are, these 2 pick and places are pick and place here, and the other are picking it and putting it back in the bin. And this was our HMI. This is how the machine prototype should look. Okay, I'll give you my contacts. You may talk about how you don't get it, because I was in the same situation. Now, when the pallet moves, then the walking beam would move and it would stop. The locking beam would get up and engage the pallet so that the pick and place happens without moving. Because when you have to pick and place it, you have to keep the pallet stationary. If the pallet keeps on shaking and moving, then you will not be able to achieve the accuracy of placing the component. So that is done by a separate mechanism. again the docking beam will disengage and it will come down, and the walking beam would come back and take the next pallet. So it would happen this way. That was me, by the way. So suppose this is one pallet, it would go on the line and it would get up for the operation to happen and then disengage, and again this would stay there, the walking beam would come so that the next pallet goes on the line. It is a bit difficult. Are you guys getting it? Yes. Okay. So here we have 3 cams. One does the pick and place, and the remaining 2 cams are mechanically coupled. One will do the rise and fall for the inspection, and the other does the locking of pallets. So when you have, this is one part that you have designed as again to see as a quality check whether the parts are placed or not. So if you just keep this separate, one cam pick and place coupled to the locking beam. So when you want to reduce the speed of the entire machine, the pick and place and the moving of the pallets on the conveyor reduces simultaneously. So when you see that I want the speed to be lower, then the entire setup will slow down because everything is synchronized and mechanically coupled and electronically coupled as well. So everything happens at the same time. And how do the servo motors, they are also talking to each other through the encoders, and when the moving pallet tells that I am going to slow down, then it tells the main cam also, okay, my pallets are going to slow down, so you better slow down your pick and place mechanism as well. So the pick and place also slows down. So the entire machine slows down and picks up pace at the same time. So everything is pretty synchronized. Now we go to the next slide. So as how we build a machine. Now when you build a machine, there are different phases that we constitute to build a machine. We start from what we want in a machine to how we are going to build that, then what are the different elements and functions we would need to build the machine. When we start with a list, a simple list as to what all things should we consider when we build the machine. Now when you talk of requirement list and gap list, a requirement list both together would tell us the machine specification. Okay, so generally when you want to say, okay, I'll relate this example with cooking because that is the simplest example that you can take. When you want to cook something, say make a cake, okay, so you'd want some eggs, some flour, some sugar, so all that is your list. So everything that goes inside building it would be the requirement list, and suppose you don't have something that you would need still, that will be gone into the gap list. So these are things, both of these together would tell us what would be needed in the machine. So both of these together when they come, then we have a list which is prepared the technical specifications of the machine, telling us to what, the temperature that would be there in the machine, to what degree the temperature should be there, what are the environmental conditions the machine should withstand, and what would be the power requirement of the machine, both AC, DC, what would be the, say the air pressure requirement or the anything that goes into powering of the machine, or what would be the ergonomics, what would be the safety considerations, what would be the length, breadth, height, the structure, what would be the material that would be processed, everything that goes is the machine specifications. Then we talk about concept generation, that is like, okay, I'll go one by one, that is why I designed those links. Okay, so you have the requirement list here. Now in requirement list, these are the main criteria that you design when you make your requirement list. So you have the kinematics, as in how and when motion will take place in your machine. Would you achieve motion using a motor? Would you achieve motion using pneumatics? Would you achieve using any other form of energy? All those which goes into how motion is achieved will be your kinematics. Material, when we talk of material, it's like which material is going to be processed inside the machine, what is the material science behind it, what all is it compatible with the material that you will be using in designing your machine. So all those will go into the type of the category of materials. When you talk of signals, it's like what all signals will the machine will tell you and how you will be processing those signals. Like say you have different controllers in the machine, different devices. One talks in say English and the other will talk in Bengali or any other language, Marathi. So how do you process all those and make everyone talk in a common language so that they understand each other. Then you have safety and ergonomics. That is a very auxiliary thing, but still it's very important when you talk of in a machine design. How do you say that your machine is safe? To what category is your machine safe? And how safe will it be if a person is standing at, say, this much close or even this much close? Is the machine safe, or will it attack you? It doesn't really attack you, but how does this, how will your machine respond to any humans coming close to your machine? Then you talk about ergonomics. Then if an operator who is operating your machine for, say, 8 hours in his shift, how comfortable will he be or will she be doing whatever is required of him in the machine? Then you talk of geometry. Now in geometry, how your machine will be like, what is the length, breadth, the structure that I was talking about. Then we talk of production. How many components or parts per minute is your machine required to produce in one day, in one shift, in 1 hour, in 1 minute. So you break it down to that much of production. So that production is like the entire cycle time is built around how much production or how much volumes you're talking of at the end of the day. Then there's the quality control. Now most of our machines would have built-in okay, not okay parts. So when you talk of machine, your machine after processing of the material should be able to tell whether it's a good thing or a bad thing. Like if you process this bottle, at the end of the day, is the bottle functional? How do you know that? You have to do tests. So is this bottle like anything, vibration resistant, that resistant, this resistant, is water leaking through it? All these, is it a good bottle or a bad bottle? At the end of the day, you have to do quality check. So finally, you have these built in, and then you tell this is a good bottle, and then you pass through it in the assembly line. And then you have assembly. So we have a different session altogether, which I'm not taking today, on machine design for assembly. So design for assembly is also a new thing. It's like you have to design your machine in such a way that assembly is easier down the line. Because at the end of the day, every machine is not a concept on paper. It has to come down to your shop floor. It has to be designed. It has to be assembled. So everything that you design in your machine, all the things that you think of, should be easily manufactured. I mean, it should be easily manufacturable, and it should be easily be used for assembly. So tomorrow, when your assembly person is telling that this design is not working, there's no easy assembly in it. So that is something wrong that you have done in your design process, that you have not thought designing for the assembly. Now transport is how you have designed your machine for transport. Like in Titan, we do not build the entire setup as one machine. It has to be disconnected, it has to be packed so that it can be sent to the customer place. So suppose you design this entire setup. So at the end of the day, it should be designed in such a fashion that when you cut it up, you don't generally cut it. You have to design it so that it's disconnected, and then you connect everything and can be transported easily. So everything has to be connected and still be independent of each other, so that transport becomes easier. And then what all the operations would be required, how the maintenance will be done, all these things you have to consider when you are building the machine, and of course the cost, because at the end of the day, we talk of money. Now, there is something called machine parameters. There are lots of machine parameters. One of them is OEE, or overall equipment effectiveness. So, have you people heard of OEE? No? Okay. So, OEE will be the product of availability, performance and quality. So, what do you guys understand by effectiveness? When do you say a machine is effective at the end of the day? Or anything is effective? Okay guys, speak.
It is producing good quality,
fulfills the purpose for which it is designed.
Alright, nice. Thanks for talking, I'm so happy. Okay. So, when you have 3 different parameters that we consider when we talk about OEE, and OEE is a very important talk when you design a machine. Now, OEE is the product of these things. So, when you talk of availability, it means how much is the operating time and what was the planned production time. The planned production time would be like, I want my machine to run in the shop floor for 8 hours. When I say 8 hours, does the machine actually run for 8 hours? Very few machines would actually run for 8 hours continuously till the last second. So how much have you designed the machine for? When we talk of 8 hours, we generally design the machine so it can sustain running for a period higher than 8 hours. because there will always be, the temperature goes very high and then you may have to stop the machine for some time and all those things may happen. So you have to take that into consideration, that the machine should be available for production for a period of 8 hours. Now, when you talk of performance, what is the ideal cycle time that you have manufactured the machine keeping in mind, and what is the total operating time? Suppose you say that I have manufactured the machine so that every time the cycle time of one product that comes out of the line should be 1 second. Now you have to test it continuously for days together, continuously running, so that you see that every time it gives that performance. It gives every time one product should come out in 1 second. Because when ideally what happens is, when your machine is, you test a machine, it may give 1 second. But then if you test it continuously for 4 hours, you may not know what breakdown going to happen, and then it may not come out in 1 second at the end of the day. So that is also comes in performance. And quality is all about good and bad. How many bad parts it's producing and how many good parts it's producing. Because at the end of the day, when we talk of production, we talk of only the good parts. We don't talk, okay, I have produced like 20 bottles and out of which 5 are bad. So you can't really use them. So that is what a good differentiates the good from the bad. So when you take all of these into consideration and multiply them all together, you get the OEE of the machine. Now generally OEE is never 100%, you never get all of these rights in real time. So generally we look at OEE of suppose greater than say 85, or OEE of 95% is really good. But that you achieve a OEE of 95%, that means the machine is always available, it's always producing high performance, and it has really good parts coming out of the machine. So in Titan we have a set OEE of 80. Thanks for asking a question. Anybody else has anything to ask? Yes, sir.
You mentioned that network diagram in concept design.
Yeah, I'll tell about that. It comes.
What is the relationship between OEE and availability, performance and quality? We have a formula for it?
Yes. OEE is the product of these things. OEE will be the product of the availability, the performance and the quality. So you multiply all these three together, and first of all initially they are calculated like division, multiplication, everything, and finally you multiply everything together and you take the OEE. So OEE is also decided prior to your signing the NDA form. So you have to tell your customer that what is the OEE you are looking at, and then you tell, okay, now it is closed. Now in WBC,
what is the time period
yes,
on which, for example, good pieces by total pieces?
Yes, sir.
What is the time period you measure it at?
Okay, the time.
What is the cycle?
A cycle. A
It's
cycle
over
is.
1 month or 1 year or 1
No.
month?
Okay, the time period during which OEE is measured. OEE is measured continuously on a real-time basis. So when you generally OEE is measured for, you can say a set time for you, because I want a OEE measured for 1 day, or you want a OEE measured for 1 period, 1 month. So you can set it at, you can have the basis. And generally we display the OEE on the HMI itself, so that you know what is the OEE that the machine is giving, and then you can reset your OEE so that it starts calculating it again. During the start till the period, what has been the effectiveness of the machine, you should be able to know it.
But will it not be standardized?
Pardon me,
See,
sir?
if somebody measures it over 1 day, somebody measures over 1 month,
It
these
has,
two are not comparable figures.
Yeah, you don't consider OEE like 1 day's OEE to 1 month's OEE. We consider like Tuesday's OEE to Friday's OEE, or July's OEE to August's OEE. It's not like I am seeing OEE of July, so tomorrow I'll see the OEE of September, how is it going, so where is the fault in the machine?
This good and bad distinction is for
part.
individual part inspection, or for sample inspection it would not
For
differ.
which inspection? It is like when you have the production going on, after each product that comes out of your machine, at the last station we generally say that you do the inspection here, or the quality check. So
If inspection is for individual piece, then only good and bad can
yeah,
be considered.
inspection is for individual piece.
Sometimes sample inspection is very
No, when we talk of inspection, that has to be built in. A quality inspection, that is a part of the machine. Then each piece is inspected. The sample inspection that you're saying is, I have not generally come across any machine with just sample inspection.
sometimes destructive testing is required. Then
Yeah.
in that case, sample testing is carried out.
Yeah, that is like all the products are made, and then you pick up one product out of the lot and then you do the testing on it. So that is like a totally different scenario. In talking about as a general every day when the machine is running, every day you have to know each part whether it is good or bad. Because each part that comes out of your machine at the end of the day, you should have that certificate of quality built in. So you know that each part that comes out is good or bad. The sample testing, when we talk, the machine is closed now, I want to just test a product, now pick it up and see whether it's good or bad. When we talk of OE, every time whether the product that comes out is good or bad. It's like that. Yeah.
What's the difference between OEE and QA, quality assurance?
Quality assurance is, we talk of in a machine's perspective. Like before the machine goes out to the customer, we take many things into consideration for quality assurance. Like even the finish of the machine, how does it look from the outside? Or how much is the wear and tear of the machine? Now all the wires have been ducted or routed properly or not. Everything goes into quality. Quality is we have a separate list for all that. Like everything has to be marked, labeled, and no edges also, that if you just brush through your machine, your shirt should not get torn. That's also a quality assurance. So everything when you talk about as a complete list, that is when we talk about quality. Generally OE is like your machine is working standing isolated. We don't see how beautiful it is looking or how dangerous it is. We just see what is the effectiveness of the machine. For whatever we have invested in the machine, is the machine giving the end result or not? That is when we talk of OE. Did I answer your question there?
Both OE and the quality both are interrelated.
Quality, OE will be a part of quality. Quality is a very huge.
Part of OE.
Yeah,
What is the relationship of OE and a 5S system?
And
5S.
5S. Okay, 5S when we talk about, it is generally in a workplace. Yeah, we consider 5S. You may say those safety, sorting and all, which I still don't remember. We have been taught to tell so many times. So these are we generally talk of in a scenario. When we talk of OE, it is like your machine is there. I have invested $5 in my machine. So do I get the worth of $5 inside it? Is the machine giving me the end result that I have brought in it to give? That is when we talk of effectiveness. Yeah, it's kind of productivity. Okay, any more questions?
One question, good
Yes, sir.
pieces.
Yes,
You
sir.
mean acceptable pieces?
Yes,
Good
yes.
is an analog scale.
No, it's not an analog scale.
But you have some limit.
Yeah. We have, it depends, like good can be anything. For example, if I want to say that this bottle is good and I'm the customer, I define that if my bottle, if suppose the length of this bottle should be 5 mm. So every time a bottle, okay, when we talk of engineering, we always talk of tolerances. So it cannot be exact 5 mm. So every time we give a tolerance that this bottle should come out with a height of 5 plus minus say 20 micron. So every time it comes on at plus minus 20 micron, that's a good part. And every time it goes beyond the boundary, that's a bad part. So it can be analog or digital.
Good means acceptable.
Yes, good, acceptable. Good and bad generally we tell in a very cliched, in a very standard terms. This is good, this is bad. That's it. Yes, that is right. Yeah, that is right. The words that we use is okay, not okay. Because okay still gives a good feeling that it's okay. Okay, any more questions till here? Okay, so this is the requirement list of WBC. The machine was designed as automatic with a cycle time of 1.2 and the component we used for testing was a nut. And the input part feeding system was a vibratory bowl. You have come across vibratory bowls? Okay, the one that you saw there was a vibratory bowl. It's just that there is a bowl and it rotates. Every time it rotates, not actually rotates, it vibrates. So every time it vibrates, the part goes from one point to another and it keeps shifting till it comes to the last point where it needs to be singulated. You've heard of singulation? Singulate is taking one piece, singling it out from the rest of the pieces. That is when you call singulation. So you keep on feeding those parts and it gets singulated at one point. So that is when you have the feeding system is called a vibratory bowl. And safety is there is different safety between operators and machine safety. So operators would be when the operator comes in contact with the machine, how do you want your machine to react? If your machine has a door, do you want your machine to open the door or do you want your machine to not open the door? And then you talk of poke okay. Have you come across poke okay?
Means never entered wrong.
Yeah.
Chip, SIM card.
Right. So anything, even this USB cable, none of us will try putting the USB cable in any other slot than the USB, even if you don't know whether it's a USB, because this is designed using poke okay. And you will never try entering this part inside your laptop, because all that has been taken care in design. So when we design a machine, you should be sure that even a person who has never come across anything of your machine should be able to work with the machine. Then the critical processes for mechanical were walking beam, locking beam, the pallet design and the cam, because each time it has to happen at the exact time that it was designed for and with a high degree of reliability. Then electrical was when we has to do the synchronization of different elements to make it work with the same speed every time. When I talk of ergonomics, there's many, ergonomics again is a very vast session. So generally we talk about height, the loading height as to which operator of my size should also be able to operate the machine. And the HMI also should be at such a height that I am able to see it without straining my neck. Are you understanding? Yes. Okay. Then that is for machine specification. When you talk of concept generation, we see how do we build the concept. Like was the solution already known to us? In this case it was not. Many times the customer will give a repeat order when you already know that this is how it has to be done, so you leave the concept altogether. But when you have to begin a new thing, then you have to design what type of concept you have to think. And generally when we talk of concepts, we talk about how to do a thing rather than the already established solutions to do it. Because when we say that you have to design a way of securing a car to protect it from the thieves and weather, you do not say of designing a garage door. You do not say that I want this type of solution. You will say I want a generic solution for, suppose I want to secure this piece onto my pallet. That's all you will say. You will not say that you design a clamping device, because that's when you limit your thoughts. So concept design is when you just unravel your thoughts and let it wander. Then we talk of functions. Now a function will be what all things are to be done inside your machine, whether your machine is doing the conversion of material, energy or the conversion of signal. Most of these processes are interconnected and happen all together in the machine. And then what you are going to achieve by doing this. Suppose you want to say that I want to move my pallet from one point to another, so that is a function. Now in a concept design for WBC, we were doing assembly. It's a part of the concept design. Now assembly has three functions: singulate, transfer and assemble. Singulate is you have to singulate each part that comes out and you have to transfer it from one part to another and you have to assemble these three things. So singulation can be done using different methods. In singulation you have to use a feeding system, you have to use a singulation cylinder, you have to use a component presence sensor to know that the component is present every time you want to singulate it. And then you have transfer, you have to transfer those components from one part to another for processing. And then you have assemble. So all these things when you talk about as an entire system, then you have the assembly of components. Any questions still there? Okay. So when we talk of concepts, then next step that we go on is the solution. Now there are different functions that are there. There's singulation, there's transfer, there's assembly. Using a singulation can be done using vibratory bowl feed, it can be done using something else also. Transfer can be done using any type of conveyors that you want. There are different types of conveyors. I am not an expert in conveyors. And there's a flat belt conveyor, a plastic chain conveyor, a round conveyor and many things which I have forgotten. And then there's assembly of components which can be done, as I said, using pneumatics, robotics, cam, pick and place. So we combine all of these and then decide which is the best solution to be taken up during whatever process you want. For our case, we had taken up vibratory bowl feeder, then flat belt conveyor and cam, pick and place. So we put all of these together and we generally award some marks. This solution will get say 20 marks, this will get 18 marks. So when this solution is the best in all terms, then we pick up this solution for the further design. Yeah, that was supposed to be. Yeah, no, that's I forgot to edit it. That was supposed to be some magazine feeder.
In the last one, pneumatic pick place and robotic pick place, they may be the same.
No, pneumatic pick place is
Robotic place.
not the same. Not the same.
They may be different, yeah.
Pneumatic is cylinders. You may not require robots in cylinders. In cylinders,
Pneumatic gripper will be there and gripper may be pneumatic operated or.
yeah, it's not like completely independent of each other. That cannot be done. Pneumatics are generally will not use robots when we talk about pneumatic pick and place. The entire process is done in pneumatic cylinders and pneumatic grippers. When we talk of robotic pick and place, yes, there will be robots, but there may not be cylinders. There may be pneumatic grippers at the end of the arms. And then we have cam. In cam also we have still used pneumatic cylinders and pneumatic grippers because the grippers cannot be avoided altogether. Then there are vacuum grippers also, but each will have pneumatics. Now to answer your question, so this is the network diagram. Now here you talk about how your PLC as in, you understand what's a PLC? I guess this has already been a session. Yeah, so how is your brain talking to different parts of your body is when you have a network diagram. So for this, the entire controller should understand what other devices are speaking of. If they don't understand, they should have an interpreter in between so that you can talk English and I can still understand English in my Hindi. It's like that. So there's a gateway in between to convert everything, and each one will have an address which is given. So if I want something from you, you're sending it from, say, house number A. I know that everything that comes from house number A is coming from you. It's like that. Any questions till this? Okay. This is an example of the WBC network diagram. That's the PLC there, and you have the HMI here, the motors here. This is the VFD for controlling these motors. These are distribution boxes for sensors. So you connect your sensor to this. Everything is already fed into this. And then you connect it using different sensors. This is the valve kit that we have here to control the pneumatic cylinders. And this is one more reed switch. Like it's a proximity sensor for your cylinder to know where your cylinder is at any point of time. This is a part of the WBC network diagram. So that brings us to the end of concept generation. The next thing that we have is embodiment design. So in embodiment design, we give specifications of each element that goes inside the machine. So you have to do calculations, you have to know what is happening at each point of time, you have to draw a cycle time chart. Then there's a sequence of operation to tell you that you should do this operation at this point of time. And you have the safety circuit design. And after which there are two processes called DFMEA and RA. That is design failure mode effect analysis and risk assessment. So these are the two things that we do after the end of the embodiment design to know where our design stands if something goes wrong with it. And what is the risk that the operator is exposed to. Now this was the design done on paper for this. This is how crude we are, we draw without scales. So this is like the entire body of the machine, that is the control panel over there. Now when we draw a machine, we divide the machine into different assemblies. Assemblies is like a group of independent systems. So when you design, say, a bottle, this will be maybe called the cap assembly, this is the bottle assembly, and this is the label assembly. So you bring all of those assemblies together, sub-assemblies together, and you design the bottle. This was the circuit diagram. I'm sorry for the neatness of it, a part of it was in my hands. So you may not understand anything. These are the VFDs, these are the motors. There are the safety things. We try to put everything on paper on one page so that when we talk about it tomorrow, we understand what is happening and how it is all connected. When you draw a circuit diagram, this is not how you draw it. You draw it much better and cleaner. So generally we do the power calculation. Most of you are aware of power calculation. We see how much DC is required and how much AC is required, and then the AC should be able to supply the DC, so you have to have a SMPS inside it. And of course, we have to divide the AC in different phases, so one phase does not get overloaded. It's a very simple concept. I shouldn't be talking about it. Then you have the sequence of operation. What happened? This is a part of it. The sequence of operation is larger. first you start, and then it can be started 2 occasions. You might stop during the event of power failure, or you might start from fresh. So it can start from a new cycle, or it can start from a previous cycle. Then all of those things, the main cam motor, the indexing motor, everything gets synchronized, and they match whatever speed you want the motor to run at. And then the processes start happening. So the pick and place motor and the rise and fall cam, it starts operating, and you have an encoder which detects the position of the cam at one point of time. It feeds it back to the master, so everything is synchronized, and then it starts happening. Okay, any questions still here? There will be a lot of questions. I'll give you my contact for that. So here is how we draw a cycle time chart. This is like a kind of thing that we have designed on Excel. So these are different things that you have. You have the walking beam. It engages with the pallet. It does the forward stroke. It disengages with the pallet. It does the return stroke. So this is how the walking beam works. And this is how we have divided into small time periods, so that you know exactly at suppose 0.15 second where my cam is, where my encoder is, where my motor is, so that accordingly you design the processes down the end of the line. This is the cycle time breakup of the walking beam assembly. There are 5 assemblies in the WBC. Do you people get this? Now we talk of safety. There's a cartoon that is there. Should I show it or not? Do I have time for that? Or I may send the link, you will see it later. When we talk of safety, there are different ways in which you design safety. One of the ways, according to ISO 13849, is this one. You divide the category of safety into the performance levels, and you talk of it as performance level A to E. Now, when you say the machine should start, then what is the severity of injury that might occur? Will it be reversible or will it be irreversible? Irreversible also includes death. So next is, if it is reversible or irreversible, what is the frequency of the exposure? How often will the operator or whoever comes near will be exposed to such dangerous things happening? Will it be like seldom or rarely, or will it be frequent? So that is also divided into F1 and F2. Then you talk about P, that is the possibility of avoiding the hazard altogether. Is there a possibility that it can be avoided, or this will keep on happening every time? Then that is what we talk about P1 and P2. Now everything that comes under the category of S1, F1 and P1 will fall under A. Then the remaining things will fall accordingly. So everything that you design in a machine should have a category that is given to it, a performance level that is given to it. So if I say that it will be already specified, like my machine should fall under the category of C, because all my processes are like, they are very severe, injury can happen, and the frequency of exposure is very high, and there is slight possibility of avoiding it. So it will fall under, say, C. So all your components, all your safety systems that go tomorrow inside your machine should abide by the standard of C. So everything should go, that should have that, whatever you design, whatever component go inside it should abide by the performance level C. So when you have any safety component, any safety systems, are any of these here? No, I believe. Okay. So if you have any safety PLC or any safety relay or anything, the standard will already be mentioned in it, that this is the standard that is followed in this performance level that is followed. So the highest performance level is E. That means the performance level E will work at a very high speed, which will give a continuous, very good performance, and it should be able to avoid these things. So at the end of the day, the operator, whoever comes in contact with the machine, is safe. So that is how you define the safety of a machine. Now,
you designed your machine as for which level?
Pardon me, sir?
A to E, what is your?
So it is completely dependent on the process. It is, we see what is the process that is happening. Say we have any simple thing, suppose you have pick and place happening. Pick and place, what is the maximum that can happen is the pneumatic cylinder, whatever, can come and touch your hand. If it is like a small injury, then you need not need E. But suppose laser marking or something that is very, very harmful is being happened, then you have to go with a higher thing, a higher standard. So generally laser marking, the whatever the shield or everything, the door will be closed and you will not be able to see it so that nobody comes in contact with it. That is when you have a higher performance level. So it completely depends on the process that is actually happening inside your machine. Any questions still there? Now we talk about risk assessment. Now this is the procedure of risk assessment that we follow. Is our machine safe? What is the definition of the machine limits? Like till what limit the machine should go, and like what is the suppose you have a robo, so this is my area to which the robo should operate, it should not go beyond this. It's like that. Then potential hazards, what can go wrong in the machine and how do you plan to eliminate it? Have you tried of evaluating your risk? And then finally, is the machine safe, or if it is not safe, then how do you reduce the risk? So this is how we take the process of risk assessment. This is just a flow chart. We have like this thing developed for that. So suppose you have loading of component happening where you have a press. So when the component loads the product and you have a press coming to hit the product, then what can go wrong is unintended startup can happen. Someone may press the start button while you are loading the component. So what can be done for that? You can give a door sensor, a door-to-door feedback sensor, that you may close the door so that when the process is happening, nobody will be able to open the door. Or you may give the condition like when you open the door, the process should stop. All those things we take into consideration during risk. Are you people understanding? Right? Then you have design failure mode effect analysis. What can go wrong in your machine? You may be a very expert designer, but there are many things that can go wrong inside a machine which we have not thought of. Generally we talk about when we have an indexing operation carrying out, then what happened in high-speed chassis was whenever the indexing would start automatically, even when there may not be pallet on the conveyor. So if someone places the pallet, then it automatically starts happening, and when there is no pallet, still the components are being singulated and you have the components rolling all over the conveyor. So then we put the component presence sensor, the pallet presence sensor, so you know that only when a pallet is there, the process should start. So all these things you should have the foresight to understand what things can go wrong. Many design changes happen even after coming to shop floor, especially in R&D projects, because nobody really understands when what can go wrong. And then you have a severity occurrence number that is given, how much is the severity of the wrong happening, how many times it can happen, and then it goes on into multiplying it both together and you have a Sun number, and then you say if the design is safe or it is not safe or what can go wrong. So there are different procedures and many things that we follow in our company. That we come to the end of these 3 stages. And we go into detailed design. Detailed design would generally include the 3D modeling of your system, how each product that comes out of your machine, how it will look like in any 3D modeling software, say Inventor, Autodesk. Then what is the pneumatic circuit of your machine, how different valves and cylinders are connected to each other. Then what is the air consumption, how much will be the compressed air requirements of your machine. Then there will be the power calculation, how much power will be required, what all switch gears you will be using, what is the I/O list, what are the inputs and what are the outputs that come out of your machine, and what is the circuit diagram in your machine. This is circuit design. In circuit design, we talk about many different things, the wiring diagram, the bill of materials, as in what all things would go inside the machine. The bill of materials also includes your the smallest wire and the smallest lug that goes inside the machine, the smallest screw, everything is there in the bill of materials, so that at the end of the day, if something goes wrong, you know how to replace it. Then there is a cable color codes. Each cable has a color code of its own, stating whether it's DC or AC or which phase it is, whether it's neutral or earth. Then you have the panel and the HMI layout. This layout that you see there is also designed before and then it's plugged in, everything, like where each part comes, so that tomorrow if you don't have space, you needn't shift from one place to another. Then you have machine ballooning. I'll show an example of that. This is how a wiring diagram is in the software, and many of us from industry will also recognize the software. These are the VFDs and these are the motors, and all these have to be connected inside the connectors inside a box. So each of these has to be explicitly specified in the circuit, so that when tomorrow the machine goes for assembly, the assembly person shouldn't imagine and connect things. Everything has to be put on paper and then it shall be connected. Then you have assembly. In assembly, you put labels in different parts where you want, like this bottle I want to be named as A1, so I will put it at A1. Everywhere in all documents it should be called as A1. So that is what it makes it easier to identify it tomorrow. And then we have a spare parts list. So everything goes wrong, you have a spare part for that. And offline programming is done. This is when the machine is in assembly, you do the offline programming to, offline would be like you're not connected to the machine then, but you have the sequence with you. So you can program that this part should happen at this instant of time, or this thing should happen then, so you can program everything. And the machine sub-assembly, you combine all the sub-assemblies, each sub-assembly is independent and produced separately and then combine together to have the machine assembly. And then we give a machine manual. It's like the fridge or the washing machine manual that you get, the thank you for purchasing our product. It's like that. This is an example of machine ballooning. Why it's called ballooning is these are supposed to be put in circles to make it easier for the assembly people. So this is my work partly. So these things are, everything that goes inside the sub-assembly is labeled, so that tomorrow if you want something, this has a unique identifier, it has the unique where it is located, what is the name, what is the brand, and everything is given. What is the, say, the part number, anything that goes missing tomorrow can be identified from these. This is the entire generic setup of the machine when you look from the front. This was covered, this is just the uncovered part when we do the ballooning. So we have labeled each and everything so that it becomes easier for the assembly person to assemble it, like where each part is placed in the machine. Now we have the testing. After everything, you have to keep on testing your machines to see that every sensor is, the output is coming at the right time. So for testing, we do online programming, and then any changes that have to be required. Online programming is, now you have done your programming, it is working as simulation, but you have to test it and work it in real time. Is it working with the machine? And then you update all the relevant documents. If anything goes wrong, you have to update it. Suppose tomorrow you change the name of this from A1 to A2, that has also to be updated. Then you disassemble the machine and you pack it and to send it to the customer place. And that brings us to the end of machine design as a whole. So any question that you have with respect to machine design, you can ask.
What type of color coding you are using?
We are using, pardon sir?
For example,
Earthing, we have a standards of everything, like we follow the industry standard. So for earthing, we use green, greenish yellow. It's like one cable that has green and yellow on both sides. And then AC also has a color coding, DC also has a color coding, light blue and dark blue respectively. For neutral also we have color coding. And for live wires, the color coding that we use is orange, so that those wires are live and shouldn't be touched. Okay, so that brings us to the end. Now, when we talk of automation, we generally go and what is next in automation. So, of course, automation, the concept of machine design is very dynamic. Every time a new requirement comes up, you have to change the way you have learned things. Hello, sir. Okay. And you need to, all right. You need to constantly unlearn everything, and you need to learn new things. So that all things are there in automation. And most of this learning that we have done is generally when we work with machines. That is why I told you needn't take any notes. Everything you'll find it all on the internet and everywhere. When you actually work like in the machine, then you actually know what things can come up. Like I learned about Modbus after working with Modbus. And then the next step that is coming in machine automation is Industry 4.0. How many people have heard of Industry 4.0? Like Praveen sir from Vienna would have already heard of it. Apart from that, okay. So Industry 4.0 is supposed to be the fourth industrial revolution. You've heard of industrial revolution? The days of the factories. Okay, the first industrial revolution was when the steam engines came. The second was when electrical technology came, things started moving, like things were always moving, but then with electricity. The third industrial revolution was when you have electronics built in, you have IT. The fourth industrial revolution will be when everything is connected wirelessly and talking to each other. Okay, how many people had heard of Internet of Things, IoT, right? And many of you would also already be using IoT without even knowing of it. Okay, so IoT is you walk inside your home knows that you have come down for tonight and today you want to cook veg pulao and it is ready on the table. That is how IoT is. You walk inside your car knows that it is raining outside and you are feeling a bit chilly, you want the temperature to be set at say 24. Everything is already known to each other things and everything is cross-connected wirelessly so that after 20 years from now, you don't have to deal with all the wires that we keep singing. Even charging should be wireless. So everything is talking to each other, interconnected wirelessly and still connected to a greater system so that it can be monitored from anywhere in the world is what IoT is. So when we talk of Industry 4.0, everything in industry is wirelessly connected, starting from the smallest sensor to the largest controller, so that the controller knows what is happening to the sensor at many kilometers down the automation line, and you are able to see what the controller knows sitting somewhere else, maybe somewhere else on Earth. We have not yet reached to Mars with IoT. So that is what Industry 4.0 is. I wanted to show you a YouTube video, but you can see that later. If you just go to youtube.com and type Industry 4.0, you'll be able to see what Industry 4.0 is, where everything has a sensor. Everything is a separate part of its own, but it is still interconnected. So that brings me to the end of the session. Thank you so much.